Yeah, thanks very much indeed. Thanks for the kind invitation to this wonderful meeting. Thanks to the technician for this wonderful fix. It's great to be here. And it's also great to literally see you as a three-dimensional sensation. I've become too much used to the idea that the world was two-dimensional. So in this talk, we will see in what way a single T-gate can make distributional learning hard. So one of the reasons we're here, I suppose, is that not only quantum devices promise to have advantages in certain computational tasks over classical computers, but this promise, and that's a pretty recent development, seems to be moving closer and closer to reality, creating a lot of interest in the field, mostly for good reasons, I'm tempted to say. But it does seem fair to say that the hardware development over the last years has been quite remarkable. That said, the elephant in the room, of course, is the question, can we hope noisy, realistic quantum devices to provide some sort of speed up over classical computers? Now, for very simple paradigmatic problems, that seems to be the case. There is quantum advantages for simple sampling problems, which are the most basic problems where one goes into the lab, not me, never let a theorist into the lab, somebody else goes into the lab and takes the raw data giving rise to a sampling experiment natively. And there's very natural and delicately tuned sampling experiments for which one can show that classical sampling up to a constant error in the total variation distance is hard, but you can, or other people can do the experiment in the quantum lab. So this cannot only be done, but has been done to great visibility, and we've heard wonderful experimental results over this week on sampling experiments of this type. But there's a lot to say about this. We just put out a long and winding review article on that matter, looking at all the complexity theory and the fine print of verification with all its ups and downs. We know that linear cross-entropy benchmarking is sample efficient but computationally inefficient. There's these obstructions of black box verification, giving rise to a bit of an ironic structure. And also Scott has, in his nice talk yesterday, mentioned the kind of subtleties of verification of quantum advantages. Now that's very good, that's very encouraging, surely, but well, it's rather a kind of a setup to sharpen the mind or the experiments. It's, to be fair, not really an application in its own right. So how do we move on and think further? So that's encouraging, but what next? So it depends a bit on who you ask. Like if you're a bit more physicsy minded, you would think that programmable quantum simulators are a very nice way forward that are somewhat intermediate between digital quantum computers on the one side and analog quantum simulators on the other side. And we've seen wonderful talks along these lines in this week. That's nice. When you speak late at a meeting, you can make reference to earlier meetings, to earlier talks. Then on the more algorithmic side, you can think of variational quantum algorithms that would tackle problems, say, in quantum chemistry, or would provide, so we hope, reasonable or even good approximations to problems in combinatorial optimization. And one could think, and that's what's coming now, of what could be called quantum-assisted machine learning. Indeed, this is what we focus on for the rest of the talk. And this is not such an unreasonable idea. After all, it seems fair to say that machine learning, it's hard to deny, has changed the world we live in. It's like ubiquitous in absolutely any kind of speech or pattern recognition, in any way of data-driven approach that takes data and makes reasonable predictions based on these data. In the supervised and unsupervised learning flavor, in all of its readings. Now, given the success of machine learning in data-driven approaches and the idea that we now have devices that may do something interesting, or may not, but let's see, it's a very reasonable idea to think in what way algorithms for machine learning could possibly be improved using quantum devices in one way or the other. So in other words, is there a scope for quantum-assisted machine learning? And that's the question we will ask in this talk. From a slightly pedantic perspective, but I'm half German, I'm perfectly happy to be pedantic. So, as there's evidence using variational quantum algorithms that there might be something there, that there could be improved performance of algorithms of this kind, we asked, what is the scope? Can you prove things about this? And we asked, like, well, ideally, we would like to have rigorous guarantees for state-of-the-art learning algorithms that are acting on real-world data sets. That's a kind of a dream, but I'm still young enough to dream. So this is what we want, to have a kind of a performance guarantee of quantum algorithms over classical algorithms. Even better, but let's maybe go more into detail, but I mean, what we mean is like data sets, like real data sets, pictures of cats and dogs, that are ubiquitous in that context, stock market data, you name it. Then you run them on an algorithm like stochastic gradient descent, expectation maximization or so, within a certain model, neural networks, parameterized quantum circuits that we like so much, probabilistic graphical models, and then we want a quantum advantage of a kind. What does that mean? What is a quantum advantage? This can mean many things. It can be an advantage in sample complexity, meaning you take fewer samples, fewer pictures of cats and dogs to make a prediction. It could be an advantage in computational complexity, meaning you are faster in doing the learning task. Or you could be better concerning generalization bounds or guarantees for the performance of an algorithm for unseen data. This could all be a quantum advantage of a kind. Now, even better, you could even think of dreaming of classical lower bounds, like pushing from below, and quantum upper bounds. So in a way, be like very specific on the algorithm. You run a very specific, say, stochastic gradient descent on your favorite variational quantum eigensolver, and a very specific model of a parameterized quantum circuit, like a concrete architecture on the one side. But you're very forgiving on the classical side and allow for all classical learners, all algorithms, and all models, and say any of those should have a certain performance. That's the sharpest possible distinction you might dream of. And this is what we want to see, and that's what we look at, but this is quite too much to be handled, and that we're not quite there yet. But what we are doing is that we are forgiving and saying, yes, we want that distinction of a very specific quantum algorithm on the one side and a generous description on the classical side on the other side, but we want to do this for like, or look at this for like fine-tuned data sets and ask whether we can make substantial progress for fine-tuned data sets. We take the liberty of kind of back engineering to, in a way, the data set we look at, but otherwise we be as stringent as we just said on the quantum over classical separation. And that's what we want to look at in the first technical part of this talk. I will be a bit shorter, but I lost a bit of time for the technical problems. On the question whether we can have a proven quantum advantage in instances of distribution learning. So what is this? So you think of a distribution being generated, a generator of a distribution. In this lingo, you would talk about concept classes, so like families of distributions that are kind of indexed by, say, kind of system size, if you want. And the generator does nothing than taking randomness. You roll the dice, and the randomness comes in, and it spits out samples from a given and well-defined distribution, pictures of cats and dogs, if you want. Now, the task of the learner is to look at this, look at these samples, and learn what's going on, and learn the distribution. This can mean many things once again. So the learner is there, it takes the samples. It could be in the context of density modeling, that is like strong simulation. The guy could want to learn the actual probability distribution that is going behind. That's called density modeling. We have something to say about this, but I will keep this a bit in the background unless you ask me about this, and have more emphasis on generator modeling, where you basically just want to create samples from the same or a pretty similar distribution after all. So the learner sits there, gets samples, and thinks about them, and spits out samples from pretty much the same distribution. This is generator learning. And the task is to learn a generator of a distribution, or rather of a family of distributions in this fashion. So can there be a quantum advantage? So in the specific setting, as I said earlier, are the distributions that are efficiently quantum generator learnable for a specific setting, for a kind of concrete algorithm on the one side, but which are not efficiently classical generator learnable no matter what you do on any classical algorithm and any classical device. Let's be slightly more pedantic here. And again, I have all freedom in the world to do that. So the setting we are in is the probably approximately correct setting, but I'm not saying anything new. It's just the same thing again. But let's go over this for a second. So the probably approximately correct or PAC learning of distribution classes is the following way. A distribution class is PAC learnable with respect to some distance if there is an algorithm such that for every distribution in that family, in that concept class, and every epsilon and delta given access to an oracle, stop. This oracle is not a Q-PEX oracle or a Q-sample oracle. One has to be careful that in this context, sometimes people are resorting to very powerful oracles, and then the surprise value in the result stems from the power of the use of the oracle. The oracle we are here is the sample oracle, which is just taking classical data. You can read, you can write, you can talk about, you can put on a sheet of paper in your head. On the hard drive, just classical data that you feed into the quantum computers. Extremely important, classical data. So no cheating with Q-sample, Q-PEX, whatever. With probability, outputs in time, poly in all the parameters, with probability of at least 1 minus delta, so probably a generator of a distribution that is nearby, so it's approximately correct. Again, it takes samples and thinks about them, and then spits out new samples of pretty much the same distribution. And that's what we have a look at. So again, can there be a quantum advantage? Are the distributions that are efficiently quantum generator learnable with respect to the Kullback-Leibniz divergence, so the relative entropy if you want, and the natural sample oracle, again, classical data on sheets of paper on the one side, but that are not efficiently classical generator learnable? That's the question we have on the desk for now. And the answer is, encouragingly, yes, there is, under a kind of technical assumption that the decisional Diffie-Hellman assumption for a group family of quadratical residues is the case, but that's a very plausible assumption in that context. And not only is there a separation, but there is an exponential separation over quantum versus classical learners in computational complexity. So the quantum learner learns exponentially faster than the classical device, and it's a proven separation for problems of this kind. It's very encouraging, I would say. That's nice. So how does that work? I'm between you and lunch, so I will not bore you with the details of the proof, although I would love to. But on the highest level, surely you have to show that it's kind of quantum hard on the one hand and quantum easy on the one hand and classically hard on the other. And the experts among you will be not too surprised to hear that the classical hardness part is actually more complicated than the quantum easiness case. That's how these problems tend to go. So on the classical side, we are standing on the shoulders of giants. In this case, the shoulders of Kearns and collaborators, who were thinking in this concept about the idea of a pseudo-random function, which is a collection of keyed functions that cannot be distinguished from uniformly random functions by any polynomial time algorithm. So on the one side, you have like on the domain, like some point, on the other one, you have uniformly sampled setting, and you cannot discriminate the two settings by any polynomial time algorithm. And yeah, these are not so easy to construct, so there's a complicated Goldreich, Goldwasser, Mikali construction to cook them up, and we have to kind of change the original arguments known, but that's kind of the upshot of this setting. And given such a pseudo-random function, or a collection of classical secure pseudo-random functions, one basically takes like seed randomness and appends the output of that pseudo-random function afterwards, that giving rise to a family of distributions that cannot be efficiently classically generator learned. So it's kind of the obstruction against classical learning of distributions of that kind. But the actual argument is more complicated than that. There's an entire reduction, polynomial reduction involved, but at the lowest end of this reduction, in the machine room of the proof, if you want, there's a discrete logarithm, there's a one-way function. I say, wait a minute, one-way functions? That's something we know in quantum information. Shor's algorithm cracks one-way functions, in particular can solve discrete log in polynomial time, as we all cherish and know. And the art form of on the quantum side is basically to use Shor's algorithm and walk this Mikali-Goldwasser tree backwards and crack the hard-to-learn distribution classes with a quantum computer. So this gives rise to the situation of having a proven quantum generator learning advantage over quantum learners over classical ones. Quantum computers can learn more efficiently, and not only that, but there's an exponential separation over the quantum versus the classical setting in computational complexity. That's great. That's very encouraging. We were very happy about this result. But to be precise, it's completely honest in the Oracle use. There's no QPEX, Q-sample, whatever. There's no cheating and no kind of dodged in whatever. It's classical data and so on. There are meaningful distributions and concept classes, but it's for a fine-tuned set of distributions, to be fair, to be very clear about this. And it's not very NISQI. It uses a full, presumably fault-tolerant quantum computer, and that may be boring for some people in the audience. But you have to start somewhere, so quantum computers can learn exponentially more efficiently distributions which are well-defined. Good. Which brings me to the second and last part. I said I would not run over time on further steps in that direction. So again, it's encouraging. We know that quantum devices can learn better, exponentially better than classical computers. This is very nice. But again, it's for fine-tuned distributions, for a full fault-tolerant quantum computer. So in the ideal world, you would like to see meaningful probabilistic modeling problems for which one can show an advantage over quantum, presumably NISQI type quantum algorithms over classical learners. And that's not so easy to get a grip at. After all, I mean, the kind of type of distributions we are thinking about, like pictures of cats and dogs, are not so easy to capture in mathematical terms. And on top of that, and to add insult to injury, the algorithms we think of, like GANs or quantum Boltzmann machines or so, they're not so easy to capture in that context. So we need a kind of a vehicle, some sort of instrument to make progress here. And what could be a better instrument than looking at the output distributions of short quantum circuits? So we go into the lab, don't worry, not me. You go into the lab and have a circuit and measure and take just the output distribution of that measurement. So you see the quantum circuit as a meaningful generator of distributions. And that makes a lot of sense. I mean, we know that in variational quantum eigensolvers, that's kind of the primitive that you're working with. You have the circuit and you take data and you massage them and put them back, or in the quantum advantage or supremacy, forbidden term, so quantum advantage schemes that we heard so much about earlier this week would be of that type. Where you have a certain algorithm and you measure. And in this context, people have been thinking about and conjecturing whether this learning would be hard in the light of the fact that sampling from these distributions is hard, as we've heard many times. There's even an obstruction of black box verification of output distributions. You cannot even see whether you are nearby, in polynomial time, with polynomial many samples. So people thought that there must be some kind of a connection between learnability, simulatability, black box verification, and so on. So we use the output distributions of quantum circuits as our model class of distribution. We want to see, can we learn the distributions of near-term short-circuit quantum computations? So can we find near-term quantum classical separations in this way? And there have been lots of conjectures around, and here we have a pretty comprehensive picture of that, which is nice as a further baby step, with ups and downs and some go theorems and no-goes and obstructions, which are kind of coming together in an interesting fashion. So first of all, they're hard to classically simulate. If they're too deep, that's what we know. I mean, that's what many talks have been around so far. Are they hard to learn? If there's very shallow, like depth 1, you have a product distribution, and they are presumably easy to learn. I look at them, now I can even go into the lab and I'm not touching anything, I learn the distribution, that should be fine. For very deep circuits, you have a full universal machine, you presumably cannot learn this, so where does hardness set in the depth of the circuit? That's kind of a question sitting around. So, a second insight here is that under a simple technical assumption, so if standard secure pseudo-random functions exist, then quantum circuits that are not very deep, like of the order of linear depth quantum circuits, is actually hard. And there's an obstruction to learning these distributions for pretty short quantum circuits. And that is true for generative and density modeling, and so learning distributions and learning, like being able to sample from the distribution in the Puck learning sense, as we've specified earlier, but both for quantum and for classical algorithms. So this time the PRFs cannot be broken by quantum algorithms. So that's kind of interesting that there's an obstruction to learnability of circuits, both for quantum and for classical learners. So the quantum machines cannot learn their own output distribution. I mean, you can't make that up, but it's kind of interesting and it's cute, but it also can be seen as a kind of an obstruction to quantum algorithms in that context, because not even the quantum machine can learn the output distribution. So that's for the sample oracle, like going to the lab and taking data and staring at data. It gets even stranger for the so-called SQ oracle, statistical query oracle, which upon taking a function would spit out in a given tau would spit out a value that's not further away than tau from the expectation value. So it's basically taking expectation value as the oracle axis. And that's something that is often used in generic machine learning algorithm, like quantum Boltzmann machines would kind of take that type of setting where you not take the raw data, but you would basically take data on the expectation value level. So how well can you learn the output distribution using SQ oracles? And here it gets even worse. It's already at logarithmic depth. It's SQ hard. So if you have a circuit that's logarithmically deep, it's hard from statistical queries. That's kind of used in generic learning algorithms. Even for log depth Clifford operations, it's SQ hard to learn the output distribution. And it's kind of weird because these are very short circuits. You can't do very much with them. And on top of that, you can, of course, you can simulate them classically, both in the weak and strong simulation sense that you have these short circuits, but you cannot SQ learn the output distribution from these very short logarithmic circuits. There's a kind of separation. There's the log regime and there's the linear regime, and they're hard depending on the fine print of the setting, but it's kind of interesting that these abstractions are sitting around. And we were intrigued about this. Yeah? We wrote a long paper that's kind of sitting on the preprint server, but then we thought, that's also giving an interesting flavor to the question of simulatability and learnability, and we wanted to look more into this connection of simulation and learning, and ask, can we put this onto a more kind of substantiated footing and kind of clean up all these ideas on if you can simulate, you can learn, if you cannot simulate, you cannot learn, or this kind of four conjectures on learning and simulation in the various readings, and looked at different settings and readings of the question, how are simulation and learning actually precisely related? And like again, looking at these various conjectures sitting around. Now, in the simulation context, what could be more natural than the output distribution of Clifford circuits? And we thought, can you learn, at least, please, learn the output distribution of Clifford circuits? And the answer is yes, you can. That's actually easy. That's a relief. So the output distribution of Clifford circuits of any depth can be efficiently learned. And the insight here is that the Clifford output distributions are uniform over affine subspaces of the finite n-dimensional vector space, finite vector space, and then you can basically do like a finite field version of a Gaussian emulation algorithm to basically undo things and learn the distribution. So these guys are classically efficiently simulatable, as we all know. It's a quantum information 101, but they're also efficiently learnable. Great. It's kind of, they're on solid footing, solid ground, and that was something we were happy about to see. But then we thought, how about adding T-gates? We know that if you have a Clifford circuit, if you add T-gates, then you can uplift this circuit to a universal quantum circuit. I mean, there's entire groups in Washington, I will not name them, who do like gate synthesis of taking a circuit and decomposing them into Cliffords and T-gates in a most resource efficient fashion. So if you add T-gates, what's happening? Now we know that if you add T-gates, you can still simulate them, both in the weak sense, where you can only sample from the distribution, and the strong sense, where you compute the output probabilities. But the effort of doing that will grow exponentially with the number of T-gates. But for any finite number of, if you have 10 T-gates, you can still both weakly and strongly simulate from the output distribution. So we thought, what happens if you add T-gates? For simulation, we know it. There's a beautiful paper by Bravi that does the best known weak simulation technique for Clifford plus T-gates. And we thought, can you still learn the output distribution of Cliffords and T-gates? And we found that strangely, a single T-gate renders learning hard. You put in a T-gate, bam, you're dead, and you cannot efficiently learn from the output distribution anymore. And the argument is kind of cute, is a reduction relating this problem to the parity learning with noise problem, where the T-gate is kind of like a noise in the algorithm. But of course, circuits with log many T-gates can be perfectly efficiently simulated, but a single T-gate makes the learning task of that already hard. That's very strange and kind of shows that learning and simulation are much more intricately and strangely related than previously anticipated. Since I'm almost done and I'm a bit short in time, I mean, I still have a lot of time left, so I take the liberty, because like 5 minutes, that's great. I cannot constrain myself of not mentioning this, sorry about this, on the power of T-gates. You know, let me go back. You know that, you know what a unitary design is. Like unitary designs are collections of finite collections of unitaries that kind of mimic the moments of the Haar measure. They're ubiquitous in quantum information in so many ways. And we know that Clifford circuits, random Clifford circuits, give rise to a 3 design, but not quite a 4 design. It's like gracefully failing to be a 4 design. Now, if you add T-gates, you can uplift the 3 design to an arbitrary order design. That's known. It's used. I mean, you've seen this a couple of times in this week. How many T-gates do you need to add to get a high order design? Now, the answer is you need a number of T-gates that is constant in the system size. So you have 10 million qubits, and you want a 27 order design. And you have your big quick Clifford circuit, and you sprinkle in 5 T-gates, and this T-gateness is kind of going all over the place, and uplifts this 3 design to a 20 order design for, 10 million qubits. It's independent of the system size. It's kind of weird, no? We were like astounded about it. So we couldn't constrain ourselves to call the preprint quantum homeopathy works, because it's like really, you have this medicine of T-gates, and it kind of can be amplified over and over again. It's still diagnostic. Although in CP we didn't dare to put it there, so that's too serious. Never mind. So the power of T-gates is quite strange. A single T-gate makes learning hard, but some T-gates also uplift designs to arbitrary order designs, which is kind of interesting. One day I will give a talk on the cup of tea or something. Never mind. The power of T-gates is interesting. So lesson, I'm almost at the end of the talk. The connection between simulation and learning is intricate. It's different than thought. It's more independent also of each other than was thought. There's ups and downs with go theorems and no-go theorems. There's abstractions improving quantum advantages in one way or the other. Sometimes not even a quantum machine can learn the output distribution of other quantum machines. So not even quantum computers are powerful enough to learn output distributions of short quantum computers, which is interesting and shows what's going on. This can also be seen as a first rigorous insight into the learnability of output distributions of short quantum circuits. There's a lot to be done. There's a long road ahead of us, but you have to start somewhere. It's a first kind of comprehensive and mathematically sound and rigorous picture of the learnability of output distributions of short quantum circuits. So in this effort, we were like a little bit guided by a nice paper by friends in Edinburgh that, to be fair, didn't have many answers. I think it's a fair thing to say, but it posed very nice and beautiful questions along this way. And because the machines we look at, short circuits, measurement followed by measurement according to the Born rule, these machines are also called quantum Boltzmann machines. And the paper they put out was called The Born Supremacy, like asking lots of questions about Born machines and the relationship to quantum supremacy. So we thought about this. That was kind of inspirational for our work. And we thought, now we've proven all these theorems on the kind of relationship between like simulation learning and the identity of the learning problem in this context, really rigorously proving these statements and understanding the identity of learning in that context. We thought, oh, that's wonderful. We should call our next paper the Born identity. Unfortunately, I didn't get this across my co-authors, so that was a dream. That's not what it's called. It's a very technical title, but never mind. Our effort was aimed at having a rigorous understanding of the learnability of outputs of quantum circuits. In order not to strain the chairman, I will not speak about this, but I should say that this is part of a larger group effort on precisely and rigorously understanding notions of learning in the quantum context. We are thinking about generalization bounds or classical surrogates of certain quantum learning models. If interested, ask me about this, but there's a bit of a wider context of learnability that's happening in our group. This is a moment, 31 minutes into the talk, of ending the talk. So in this short talk, we looked at learning tasks, and we thought in what way quantum computers could help in tackling learning tasks and make things better, and whether there's a scope of quantum-assisted machine learning from the rigorous and like precisely minded perspective, which seems timely because there's like evidence that variational quantum eigensolvers would do that in one way or the other. So we want to sit down and see, is there scope of that field, and can we do something? That was our motivation. We made progress along certain lines. In particular, we found a separation of quantum over classical learners in Park distribution learning. In fact, an exponential separation in computational complexity of the quantum over the classical learner, which is very encouraging. It shows the field exists. That's good. Quantum machines can, in principle, learn better. Yes, for fine-tuned distributions. Yes, full quantum computers, which are fault tolerant, but there is something to be done. It's very encouraging, I would say. Then we also found that if you look at short quantum circuits, what we have in everyday's lab, or you have in your lab, followed by measurements, that gives rise to a natural family of distributions. There's ups and downs, and we found lots of theorems, but there's also obstructions in learning the output distributions of local quantum circuits, which is good, but also not so good, because sometimes there's a bit of an obstruction towards looking at structural set. If you have a random circuit and you measure, it seems not too easy to make progress here. So the fully structured and fine-tuned setting is very delicate, and you have like wonderful advantages. The structureless setting of short random circuits or so is like hindered by no-go theorems and obstructions. So what keeps our further research along these lines forward is the question, good, you can go to a certain point, fine-tuned structure is good, no structure is not so good. So we've also seen that a single T-gate renders learning hard. So how much structure is needed at the end of the day to have a reliable quantum advantage of quantum over classical learners based on real-life unstructured data? And while I do not know, I would love to know. And on this note, I would like to thank you very much for your attention and looking forward to the questions you might possibly have. Thanks.